break coming up and all that excitement. But we've got a great one here today. Ahmer Raza is going to tell us about group testing and differential privacy. Two things that sound very different, but are connected, right? Mm-hmm.
Right. Technical stuff here. So we're just turn it on.
Okay.
I think. All right, go forward.
Okay, excellent.
All right. Good evening, everybody. Thanks for being here. I want to preface this by saying real quick that this was supposed to be a bit of a longer talk. My slides corrupted. I know that sounds silly, but it did. And so maybe for the best, maybe we can keep this more discussion oriented. But this talk is a bit shorter. It's probably going to be about half an hour instead of the usual 50 minutes. Just wanted to just that. So I'm Ahmer. I'm a current master's student in mathematics at Clemson, and I work under Dr. McMahon and Raphael. Under group testing and differential privacy is my project in particular. And to give a brief sort of synopsis, group testing is a way you can test massive populations really efficiently and do so in a way that's actually better than if you have tested each person individually. And we'll see what that means in a bit. And differential privacy is a way of keeping information secure. So it's a really, really strong metric for privacy. When you say privacy, what is privacy? Differential privacy is the metric, so to speak, for privacy in the 21st century. And the latter discussion is unfortunately kind of a bit short, but we'll make do. Okay, so as all mathematicians do, let's start with an example and then we'll generalize. So imagine I have 9 points. These are golden coins, they're gold, the blues. They're really heavy and they're really valuable. And somebody has replaced one of my gold coins with a fake copper coin. And we want to find which coin this is. Now, copper weighs a lot less than gold, so that's what we're going to use to figure out which of these coins is fake. And we know for sure that one of the 9 is fake. Okay? So we're given this measurement scale. What's our initial approach? What do we want to do? Sort of weigh each coin individually, right? So we can weigh the first one. That's fine. It weighs the correct amount. We weigh the second one. That weighs the correct amount. So on, so forth. And after we weigh the 8th coin, since we know that there's one coin that is fake, we can just say that the last coin is the fake one. That's what we can do. So this is like the worst case scenario. This took us 8 weighs. Now this doesn't seem too arduous, but I promise in the extrapolation in the next couple of slides, our goal is to reduce this number. We want to weigh as few times as possible for practical reasons, maybe.
Do we know the weight of the individual coin?
Yes, that's, sorry if I didn't make that clear. Gold coins are much heavier, copper coins are much lighter. So we know the weight of each individual one. Let's say it's 200 grams, that's 100 grams. Seems a bit heavy for a gold coin, but we'll see. Okay, so can you think of any way to do this more efficiently? There's a clever trick we can use. If you had a weighing scale.
Split into groups of 3.
Exactly. So instead, what we can do is we can split all the 9 coins into groups of 3. We can test the whole first group. Test, by test, I mean weigh. We can weigh the whole first group. If this weighs, what did I say, 200 grams for the gold coins? If this total group weighs 600 grams, it's fine. If it weighs anything less, all we know is that one of the 3 coins in the group is the fake one. Okay? So in one weighing, we've managed to clear all 3 of these coins, because we know that the total weight is what it should be. So that's fine. That's fine. And now we've cleared 6 coins in 2 tests. For the last group, we know that the coin is in the last group because we know there's one fake coin. So we can test each one individually, and this will take 2 more tests in the worst case, that and that. And we've managed to deduce that that is the fake coin using only 4 weighings. So we've cut the number of weighings we had to do by a factor of 2. Okay? So this extrapolates really nicely to the problem of testing large populations. So this isn't particularly large. This is 16 people, but imagine we had 1 million of them. Okay, and some of these people have a disease. In red, here 2 of the people have the disease, and the rest are fine, they're negative. And we're given a diagnostic test similar to the weighing scale. And the diagnostic test tells us whether a sample is positive or negative. A sample here could be like if you remember during COVID-19, we had to do saliva testing. Could be a blood sample, could be some sort of other biospecimen is what they call it in the jargon. So we have some sort of sample for each person in here that we can use to deduce whether or not they're positive. Okay, so the first, and our goal here is to find, for now, is to find which of these people are positive and which are negative, similar to the coin. The only difference here is there's 2 people who are positive here, and there was only 1 fake. So we want to find these 2 people who are positive. How can we do this? Using the exact same idea. So first, we split this into groups. So our goal is to find which of these people are infected with the disease. And to start off, we split these into groups. Here, groups of 4. And we test the combined sample of each group. So for each group, let's say we have 4 saliva samples. We combine all of them together into 1 sample. And we test that 1 sample. Okay? And that 1 sample tells us whether someone in that group is positive, whether someone in that group has a disease. It doesn't tell us which person, but it tells us that someone has a disease. So, for example, this group will test positive once you test the pooled sample, combined sample for all 4 people, because this guy right here is positive, even though the others are negative. So that's not very helpful for now. But if our entire group tested negative, what can we say about every single person in that group? They were all negative. They don't have the disease. So we don't have to test that group anymore, and we've saved a ton of tests. When the prevalence is just a fancy word for the proportion of people who have the disease. When the percent infection rate in the population is low, this can save a lot of tests because you've cleared out large swaths of people in your sample without having to test every single one. So this is really useful. Okay, but we still, in order to figure out which of the people within the pool is positive, you still have to test each pool. So we can subdivide again. Take our pools, the ones that had the positive in the sample, and divide them again and retest those. So we're going to divide. And these 2, remember, or these 4 pools now, we already cleared. Those were negative. So now we only have 4 pools yet to test. So we're going to do 4 more tests. This pool turned out negative because there's no people in, there's no positives in there. This one turned out positive because there's 1 guy in there who's infected. Similarly, negative and positive. So we ruled out we don't have to test these anymore, which is nice. And then finally, we're going to split 1 more time in order to really nail down who within each sample is positive. So we're going to split 1 more time. Remember, all of these gray pools, I say pools, now they're just individual people because we've split. All these gray pools have already been cleared because in previous tests, we tested their pool samples as negative. And so remember, we don't know that these 2 red people are positive. We don't have that information. That's just for your reference. So we have to test now, do 4 more tests for each of those samples. And we've classified all of the positives in the sample population. And this took us 12 tests instead of 16. Now this reduction doesn't seem like too much because in practice it's way more. And for large sample sizes, even a, what is that? Even a 16/2 reduction in tests is significant. Really significant. Okay, so group testing is a cost-effective approach for screening large populations. That's what it is. What we discussed here is called classification. Your goal with group testing here is to figure out which people are positive. what you can do instead of classification, which is also really useful and it's what we focus on, is prevalence estimation. Here, your goal is not to figure out who in the population is positive. Your goal is to get an estimate for the prevalence of the disease. By prevalence, there's two interpretations, both are equally valid, is the proportion of positives or the percent of affected people in the population. That sounds better. Or the probability of any individual testing positive. So those are the two interpretations for the prevalence. So we talked about classification. Now we're going to see how we can estimate prevalence using prevalence. And I want to note here, we had to subdivide a lot in order to classify each person. With prevalence estimation, we can actually get a really good estimate. We'll see what I mean by good in a bit, using just one level. So we just split once. And from those pooled sample results, from those ones and zeros that correspond to each pool, we can get an estimate for the prevalence, if that's our goal. So it's even fewer diagnostic tests. Does that make sense? Any questions up to this point? Okay. So why care about prevalence at all? You don't have to take my word for it. The CDC uses it for three things, and it does large-scale disease surveillance. So millions of people per month, millions of people across many different diseases. I mean, most recently was COVID-19. They did massive, large-scale surveillance. I think it was something like 75% of the population had been surveyed by the end of the pandemic. So they have three goals when they estimate prevalence. They want to figure out where they can best allocate resources. By that I mean hospitals, testing resources, sort of health-related things. They want to figure out what they can do to prevent spreads, outbreaks, way before, or during their happening, and risk anticipation. They want to figure out how they can prevent spreads way before they even happen. And for this, you want as many people in your study as possible, and this gets extremely expensive. So that's where group testing comes to the rescue, with prevalence estimation. Okay, so with prevalence estimation, it's a similar setup. We have our master sample. We don't test it just yet. We subdivide it into 4 pools, and then we combine samples within each pool and test that combined sample. That tells us the status of each pool. So let's just call those Z's for convenience. So a 1 indicates a positive pool, and a 0 indicates a negative. The question is, how do we estimate prevalence with ZJ with these four samples? Let's do a bit of math. Ignore that bottom part for now. Got the transition. The probability of a negative pool is the probability that all of its members are negative. So a negative pool only happens if all of its members are negative. Okay, so we can look at that probabilistic. Probability that all of a pool's members are negative. Well, first off, all of the members inside of a pool are independent. So we can use laws of probability. We can say that the probability that members of a pool, all members of a pool are negative, is the probability that any one of them is negative times or raised to power the pool size. So in this case, we'll call that C. In this case, C equals 4. Because we have pools of size 4. And what is the prevalence? The prevalence is the probability that any given person is positive. We don't know it, but that's what it is. That's the definition. So 1 minus the prevalence, 1 minus P, is the probability that any given person in the population is negative. So we can substitute that. So we've gotten a relationship between the probability of getting a negative pool and P, which is the probability of an individual being positive. And we can use this to make an estimate. So just some simple algebra later, I express P in terms of the probability of a negative pool, and I get this relationship. But we don't know the probability of a negative pool, and we don't know P. We want to estimate P. We don't know the probability of a negative. So we use our sample, use a sample estimate. So we just take the sample average of all of our pool statuses. These ZJs, we take the sample average, in this case it'd be 0.5. And that's how we construct an estimate for the prevalence. Does that make sense? And this has some interesting properties for those interested. This is the MLE. It's sufficient, it's strongly consistent, which means it's asymptotically unbiased as well. And so we can use this to, let's look at this specific example. We can use this to estimate the prevalence of our disease here. So plug in all our values and we get a prevalence estimate of 0.159. And a natural question is, how good is this estimate? It's not a, yeah, how good is this estimate? And before we can answer that question, there's something important needs to be said. And that's that the test result that we observe is not always 100% accurate. Tests in real life have a false positive and false negative. So it's not 100% accurate. That means there's a chance that what you observe is not the status of the pool. So here, that pool is positive because there's a positive person in there. But after testing the pooled sample, it flips to negative because of inaccuracy. So there's a sensitivity, the true positive rate of your diagnostic test, and that's the probability of a positive result, given that one of the people in your pool is positive. And you have a corresponding true negative rate. These are the accuracy of your test. Probability of getting a positive test result, given you're actually positive, and the probability of getting a negative test result, given you're actually negative. And so we can, there's a vast literature on constructing this estimator, or actually there's two papers, but there's a vast literature behind the foundations of it. Constructing this estimator, given that you have a diagnostic test that's not 100% accurate, it has this strange fella, which is the variance of the estimator. You can think of this as the precision of your estimate. How good is your estimate? Think of it like that. This is asymptotic variance, so there are a couple assumptions associated with it. But because we're in the realm of large-scale testing, these asymptotics are easily reached. So no need to ignore.
Question,
Yes,
what is J, what is S7?
I can explain that in a bit more detail. J, so in group testing, the notation I'm using is you have n people, in our case it was 16, you divide them into J pools. Size C. So that's the notation we use. Should have wrote it there. So, and R is a convenient quantity. It's a convenience quantity. That's how it's defined. If you're interested, I can talk more about it. Is that good? Okay. Okay. So that's prevalence estimation. Now I want to take a really sharp detour and ask you this question. Do you guys pay your taxes? We all pay our taxes. But if this question was presented to you, you wouldn't have, nobody would say yes. We all know what would happen if you said this. So we're all gonna answer no. What does this mean for someone who wants to learn how many people in the population evade their taxes? This means that nobody in the population is going to be evading their taxes. They're all stand-up citizens. They're all going to be paying their taxes on the planet. So how do you learn useful information? Let's take this question specifically as the example. Here's a strategy for still gaining some information from these people who don't want to admit that they don't pay taxes, but still keeping their information confidential. In what metric I'll explain in a bit. So imagine you have a coin, and this is a weighted coin. So there's a 75% chance that it's heads, just for convenience. If your answer is, if you flip the coin, if it's heads, you answer truthfully. Yes, I do evade taxes. If it's tails, you answer the opposite of the true answer. You say, no, I don't evade taxes. You actually. So this adds noise. And more importantly for the person, it adds plausible deniability, which means if the surveyor, person who's made the survey, person who's asking the question, says, wait, you answered that you do evade taxes. The person can just say, oh, I flipped the coin and I actually don't evade taxes. It made me answer the opposite of my true answer. So it adds plausible deniability. And this addition of noise is a really, really important thing in this context. Okay. So how do you quantify the privacy? How do you quantify privacy in this context? The metric to use, and yeah, after using this scheme is called randomized response. Answering the question in this manner, you can still learn useful information. Specifically, you can still learn how many people evade taxes, or percent people who evade taxes. So you can still learn useful info while keeping people's privacy secure. And the metric to quantify this is called differential privacy. With differential privacy, you say that the outputs I observe should look about the same, not given a small change in what the person answered. So here, whether the person evades taxes or doesn't evade taxes, the answer, the output of their answer, probabilistically should look about the same. What do I mean by this? I mean I can upper bound the difference, the ratio of this quantity by e to the epsilon. So there's this privacy level of epsilon. Lower epsilon means more privacy. And it's a bound on how much you can learn. So it's a really fundamental notion of privacy. It's not like encryption or any other sort of thing. It's a bound on how much you can learn, period. So to reiterate, for similar inputs, by similar I mean neighboring, and that's actually a very, very important. It's a very problem-specific definition, but there's widely accepted notions of what it means to be similar, and there's differing in one element. In our case, it's pretty obvious what it means to be similar. We say whether the person evades taxes or doesn't evade taxes. Those two are neighboring, similar. I want the output to not reveal much information about the person. This makes sense. This notation is for illustration, just the idea makes sense. So you can also think about it as the person's answers having a probability distribution. And given the true value of the person, whether the person evades taxes or doesn't evade taxes, the probability distribution should not change by more than a factor of e to the epsilon. Okay? So I had a slide on this, but it's gone. So let's work it out right now. So what I want to do is I want to bound the bound let me erase that. First off, I should stop. Any questions about privacy? What we've been discussing.
So what is M?
M is notation for the mechanism. It's like you can think of it as a random function that maps inputs to outputs. So here it maps the person's true, whether or not they actually evade status, to their answer. So this is the mechanism. This coin flip is the mechanism. Okay. Good question. Thanks for asking that. Does that sense any questions? Okay. But we would have bound this quantity, and also we can replace this with yes by e to the epsilon. Okay, so whether the person is whether the person answers yes, okay, we know the person has answered yes. If he was truly yes, and if he was truly no, we want this quantity to be less than or equal to e to the epsilon. And all combinations, so flip these two and turn these to no. So there's going to be 4 quantities we want to bound. Okay. So the first quantity is just this. The probability that a person answers yes, given that they're truly yes, and we also assume that there's some underlying probability. Let's assume person has a probability p of being truly yes. Something interesting if you've read about differential privacy or interesting. Differential privacy is a computer science concept. It's made of computer science. And there people really don't like to deal with distributions. So they do all sorts of crazy stuff that assumes a distribution, like calculating probabilities, but they only deal with realizations, never acknowledge the distribution. That's sense. But here we are. So the probability of answering yes, given that you're truly yes, we're going to answer yes, given that you're truly yes, is p times 0.75. Right? That's the probability that you're truly evading taxes. That's the probability that you answer as such. And you divide this by the probability that you answer yes, but you're truly no. So the only way that can happen is if you're truly evading taxes and you answer the opposite. And that'd be 1 minus 0.75. It's the probability of a tails, right? It would be p times or 2 times. And it simplifies to 3. So we want this quantity to be less than or equal to e to the epsilon. Okay, so that's one of our quantities. We need to do the same thing for each combination of yes and no up here. So we also want to bound. I'm going to erase this. And note, this p factor cancels out. So the privacy that you get doesn't depend on your chance of answering yes or no. So the second quantity we want to bound, let's just flip those two, flip the yes and no. Second quantity is yes. And we don't have to go through the whole thing of calculating this again, because it's just 1 over that value. Just flip the numerator and the denominator. So this is 1 over 3. We want this value to also be less than or equal to e to the epsilon to preserve epsilon differential privacy. The third quantity we want to bound is. So another. Is the probability that you answer no, given that it's true. Yes. Make sense?
Is that that person up there, is that supposed to be one? Given that,
Yes.
oh,
Thank you.
and just get.
Yeah, thanks. It's getting a bit messy. Let's just keep in mind that's a quantity we would have found. Let's collect them there. So this would be E times probability that a person is truly yes times probability that they answered no. So what would that be? What happens? Person is yes and they answered no. They got tails on them, right? So there's a probability of 0.25. Similarly for the denominator, probability that they answered no, given that they truly do not evade taxes, is 0.75. So we get 1/3 again here. Sorry, I've been writing 1/3 over and over again. No, that is 1/3. Okay. I'm a mathematician here. Okay. So it's pretty easy to show that the last quantity we want to bound is 3 again. If we just flip these two, we get 1/3, we get 3 again. So there's duplicates here, but that's fine. So the worst case, and this is what I want to emphasize, is that differential privacy is a worst case privacy bound. In the worst possible case, well, in the worst possible case, this is the privacy that you get. This is a unitless quantity, so you can compare it across different scenarios. There's no direct interpretation other than it's the problem. It's the worst case difference, worst case increase. So this is the privacy we get. Log 3. Does this example make sense?
Wouldn't it be 1 minus P? Except if it's saying answer no, because he's.
Yeah, you're right. But since they canceled out, it isn't. Thanks. Canceled out. Okay. So this is differential privacy. It's used all over the place. It's used by Google. It's used by your smartphone today. Like in this day and age, it's used by Microsoft. It's used by the US Census to collect data. So it is the metric for privacy. And it relies on this notion of changing what you want to be kept secret doesn't influence the output by too much. And by too much, I mean it's upper bounded by E to the epsilon. Epsilon is the privacy level. Lower values mean more privacy. In the most edge case, when epsilon equals 0, this is less than or equal to 1. Okay. Worst case. When epsilon equals 0, you learn nothing from the data. The data is completely useless. It's uncorrelated with the inputs. And so you have perfect privacy, but doesn't mean it because you don't learn to keep. Does that make sense? When epsilon is 0, this is less than or equal to 1, which is the worst case. This can never be this upper cannot be, epsilon can never be less than one, or less than, yeah. Epsilon can never be less than 0, because if it was, we just flip these two, because that quantity also has to be upper bound by 2. So if we had one of these ratios that was less than 1, we also have to upper bound 1 over this ratio. There. We also have to upper bound 1 over that ratio. So always epsilon has to be greater than 0, greater than or equal to 0. And when it's 0, you get perfect privacy, but it's useless. And then when, yeah, that's all I want to say. Any questions, comments, thoughts? This makes sense? So this is where my slides end, but this is not where my work ends. And what I wanted to talk about for the rest of the talk was this really interesting idea. Is that similar to randomized response that we saw earlier, group testing actually inherently provides privacy. Okay, I'm not going to say differential privacy just yet, but it provides some notion of privacy, and we can observe that. By trying to figure out a person's true disease status only using these outputs. So if you have this output, let's assume a perfect test, okay? Let's not even consider the SE and SP, this true positive rate and true negative, okay? Let's assume we have a perfect test, and this is the status of the pool of that. And it says positive. What does this tell you about this person? Does just knowing this tell you anything about that person? Gives you a probability that they're positive, but it doesn't, you don't know for sure. Even though you know this for sure, you don't know which of these people is positive. You don't even know how many. Okay? What about this pool? Assuming a perfect test. What do you learn about all 4 people? They're all negative. They have to be. If a single one of them was positive, the pool would be positive. So these positive people sort of mask other people's statuses. But these pools don't provide any privacy whatsoever. Okay? So we rely on, when I say inherent privacy, when I say group testing provides inherent privacy, there's sort of 2 sources of noise that cause privacy. Is this grouping mechanism, okay, which only provides privacy for positive pools. And I'm still not saying differential privacy, I'm still saying an intuitive form of privacy. Intuitive meaning, if you observe this, you don't know, still can't say for sure what that is. But it doesn't provide any for negatives. That's where the SC and SP come. If you observe a negative pool and your diagnostic accuracy is not 100%, there is some plausible deniability. You could say, oh, there's some chance that this pool is actually positive, and it's just been tested as negative because of the false negative rate of the test. And that's inherent to the diagnostic test that's used. So those are the 2 sources of privacy, and I'm sorry I don't have any visuals to say that. And that's really an intuitive form of privacy. And I formalized this using a couple of results in my paper. And actually, group testing does provide differential privacy in 2 notions. There's 2 notions of privacy. One is what we talked about, which is the worst case privacy. It's whether your pool is negative or positive or whatever, this is the level of privacy you get. And that level of privacy is purely dictated by the diagnostic accuracy of the test. Okay? Why is that? Because if you think about worst case privacy, what's the worst case? This is the worst case, that everyone in your pool is negative. And so when you do this change, this difference in your status, when you say, oh, when you're comparing differential privacy in pool testing, what you do is you take this pool, take an identical pool, but switch the status of one person. And you try to upper bound those ratios by e to the epsilon. And the worst case is that you compare a wholly negative pool against a pool where there's one person positive. you know exactly who that person is now, because their status dictates the status of their pool. So there's no, this notion of privacy, there's none of it just by pooling alone. You need diagnostic accuracy. Okay? There's another more probabilistic version of privacy that I've not formulated but adopted. And it's assuming that each pool has a distribution, that there's P times C. There's P times C. I don't explicitly assume this, but that's the assumption. That's the underlying assumption behind my results. Presume that P times C of the people in your pool are positive. So there's some chance, there's this P. I don't want to say that. Okay. There's this chance that you have another positive in your pool, and that adds even more noise and thus more privacy. So that's the first part of my set of results, which I can go over if anybody's interested. So the first part is that group testing provides inherent privacy to the design, which is great because I at least, don't trust large corporations to keep my data. My conspiracy theorists, that was a joke. But it's always better to provide inherent privacy, no third-party stuff, so that it's physically impossible for anybody to tamper with your information. Using inherent privacy, nobody ever observes any sensitive information. All the data that everybody ever observes is private. Okay? You could always just individually test these people and add privacy afterwards. You can perturb them, you can make them noisier. But at that point, somebody's observed it and you have to trust them. There's like a trust chain. That's also a big topic in photography, trust. So inherent privacy, that's great. And what you can also do is actually design optimal strategies. So if you want to estimate prevalence, I've got some results that dictate how you should be picking your pool size and how you can perturb these. You can change these, flip these with a certain probability after observing them to achieve a level of privacy that you want. Here, we had log-based 3 privacy. In general, for this same scheme, if instead of 0.75, I have something else, the privacy that it provides is, let's say P is the probability of flipping, okay? Let's call it Q actually, because we already had it. That's the differential privacy level you get with this. So I derived a similar bound for group testing, which is actually a surprisingly related concept to this. You can illustrate it in a similar diagram. So I derived a privacy bound analogous to this. It's significantly more complicated. But after that, I derived optimal pool sizes and ways you can perturb these pool test results to achieve a level of privacy. Like say you wanted to achieve log 3 privacy here. I'm going to tell you instantly, oh, you need Q equals 0.75. That's what your weighted point should be. If I wanted log 2 probability, it would be, you would need your Q to be 0.666 repeating in order to get that. Okay, so similar idea with group testing. And actually, interesting result. When you estimate prevalence in this way, maintaining differential privacy and with group testing, your variance in the estimator actually decreases. You get a significantly better prevalence estimate, like orders of magnitude better. For any value of the prevalence, P is the only unknown in our entire setup. And you can get significantly better estimation precision using optimal group testing if you want to achieve differential. So that's my second result, is not only does group testing provide inherent privacy, so if you wanted reasons to use group testing over individual testing for estimating prevalence, The first reason is it automatically provides better privacy and it's cheaper. Okay. But if you want to achieve a certain level of privacy, which is what happens in practice, group testing is still better. It's cheaper and it provides that level of privacy. And on top of it, it provides far better variance if you use our optimal designs. By optimal design scheme, I mean optimal pool size values and artificial noise values. And closed formulas for those. So no numericals. Was that clear enough without pictures? I'm sorry. Is that description illuminating them? So that's sort of what I do. We can talk more about it. Already. Oh no. 3 minutes in. I think I'll end it here. Thank you so much. Any questions?
Yeah, any questions? I have one, I guess. This is maybe a silly question, but I presume that if you've got your whole sample in front of you, very large sample, then doing this kind of testing, it makes most sense for all the pools to be of the same size.
Yes.
What if you can't control that? What if you're testing from all over the world? You've got somebody, what happens if the pool sizes have to vary? Have you thought about what happens there?
Yeah, that's a great question. Since differential privacy is a worst case bound, the small and since larger pool size give more privacy, your differential privacy bound would just involve the minimum pool size since it's a number. Yeah, there's no average case notion, so it's a worst case. That's a great question. And another natural extension to this is right now we're assuming that these not only increase or make the pool sizes vary. Right now, we're assuming each one of these people are in their own pool. In practice, sometimes samples get contaminated. Sometimes you want to retest to get more information. That also happens. And there's privacy loss associated. So those two are my sort of follow-up directions.
Other questions?
Yeah, so for a given epsilon value, you could be able to reconstruct the true probability of yes and no, right? I mean, they wouldn't be the same as if you had measured in the data because, you know, there was flipping going on. But you would be able to reconstruct it, right?
Yeah, well, not reconstruct, you would get an estimate.
Yeah, an estimate, but it would be around the area. You also look at, you know, but because you're using that epsilon for your privacy, that's, and you know, it's giving you a bunch of noise. So you're, like you said, you're re-estimating like what the statistics is. Do you have like extra or look at like what the what that adds to the deviation?
Yeah, so there's two scenarios. One is you're just group testing. Okay, so I'm gonna be group testing and individual testing. Individual testing is testing each person. Okay. And so the first scenario one is you don't just use some pool size and you have some diagnostic test sensitivity and specificity. So group testing provides more privacy and less cost. Well, individual testing, this is also a great point. Individual testing provides better variance for large P. If you're not using our optimal results, actually group testing can still sometimes provide better variance for small P. Okay, but group testing is much more cost effective and much more private for whatever pool size you choose. Okay. The second scenario is the design scenario. Optimal design. Where you choose optimal C. And you choose SENST. This is also really interesting. You can actually change the accuracy of the diagnostic test after observing the data, but that's besides the point. So you choose, you guys see this? You can choose optimal values for these. And in this scenario, group testing and individual testing have the same privacy. Same epsilon. But group testing always has better variance, a significantly better variance. It's significantly more cost effective. Yeah, there's no other benefit to it. Does that answer your question? This is terrible to read, I'm sorry.
My question is like, you said that you wrote papers about it. Can you share with us like the titles and where we can find it?
Yeah, sure. I need to ask my advisors if, because it's a journal paper, preprints for that journal aren't encouraged. But we're gonna be releasing it as just a PDF on my website hopefully soon.
Do you put it, I don't know what your culture is. Do you put them on your archive?
Yeah, I wanted to put them on the archive, but the journal policies.
Really? What's the journal?
It's biometric. You're considering biometrica. It's considered prior publication if you submit it to her, which is unfortunate.
Yeah, a lot of bio paper for journals are like that.
So I can share the title, the likely title, so you can search it up if interested. After publication, unfortunately.
Oh, so do they let you put it up on the archive after it's published?
That's a good question.
Don't think
No,
so.
I don't think so.
Can you put it up on your website?
Yes, I can do that. Just the PDF. So that's gonna be the title of the paper mostly. We have, I'm sure how long the event lasts. I'm presenting a poster of this research that contains all of the information. But I think it's.
Oh.
Yes.
Oh, will be like part of it is gonna be in your thesis or something like that? Because although I would not be willing to pay for the journal,
Yeah,
your thesis is gonna be available for free anyway on the Clemson website, so. If it's gonna be part of that, I might look at that.
yeah, I won't be doing a thesis, so,
Okay.
yeah, but. How to share. If you're interested, just shoot me an email. I can send you PDF of that paper once it gets published. Yeah, or even before.
Post it on the dark web. Other questions? All right, the same. Yeah. Thank you very much. That was very interesting.
I'm sorry I didn't have the slide deck. It would have been much more easy to understand.